Okay, good morning, everyone. Welcome to this new webinar from the International Energy Agency for Ethiopia. So this is still in the framework of our capacity reinforcement program on energy statistics and energy modeling. Today, we will focus on energy modeling, and we are very, very lucky to have with us our friends and partners from the University Politecnico di Milano, who have extensive experience on energy modeling and on different specific topics they will introduce to you today. And in the future, we will be able to have deeper sessions and more hands-on sessions to work on modeling tools, modeling approaches, where Polemy has expertise. But this will be the next phase when we have more time together. Just reminding you where we are in the agenda. So today is the last session of this second part of our online trainings with this presentation by Polemy, and also some housekeeping rules, but then up to you, Polemy colleagues, to define how you want to interact with the group. But you know you have the Q&A box. You can raise your hand and speak up for any question. And as always, you can send us your questions by emails when you need it. Without further ado, I just want to give the floor to you, Emmanuel, thanking you again for taking the time. And if you can maybe introduce yourselves, your work, and what Polemy has been doing, especially with Ethiopia, because I understand you have been collaborating a lot with Ethiopian universities. I'm sure that will be of interest to the participant. Thank you very much.
Thank you very much to you, Arno, and thank you for the IEA to engage us in this very interesting program. We are really honored to be part of it, and we are very honored to meet, even if so far it's a kind of virtual meeting, the colleagues that are listening to us from Ethiopia. We look forward to having the chance to meet them in person, because I think that after this 1 year of mostly global lockdown, we really look forward to have the chance to come back to do in-person meeting. So it's really a pleasure for us to be here, and I'm happy to introduce a part of our research group at the Department of Energy, Politecnico di Milano. Together with me, maybe you can switch on the camera, Nicolò. We have 3 research fellows that are deeply engaged in their research activity into modeling stuff. We have Francesco Tonini, we have Nicolò Golinucci, and Nicolò Stevanato, which I'm not able to see, but probably you can see him. Together with them, we have the goal of today. I will try to share my screen so that I will proceed straight to it. Together with my colleague, we have a couple of goals today. In the very first part of my presentation, I will recall together with you some energy and development, the link between energy and development, and also we will try to see how additional challenges in the post-COVID scenarios are a little bit changing the environment. And once we will be able to understand that, we will try to see how let's say the science of modeling can contribute to tackle these big challenges that are fastly changing over the year, and especially over the last year with this COVID emergency. Before going into them, just a couple of mention of the cooperation, the long-term cooperation that Politecnico di Milano has started with Ethiopia. I just remember a couple of things. So one was an enabling project that was started back a few years ago and during this eduling project, we have worked with the Jimma University to establish a Master of Science in Energy Engineering, together with other countries like Kenya and Tanzania. And I think it was a very interesting opportunity for me, and I was then able to understand a little bit more how the educational system works in your country. And currently speaking, another very important element we are carrying out is not only on energy, it's a broader program which is carried out by Politecnico di Milano together with other 6 Italian university, and in full synergies with the Italian embassy and with the Ministry of Higher Education in Ethiopia and in Italy. And we will deliver a master, educational master of 1 year, to young lecturers of the Ethiopian university, let's say, giving them the chance to, be engaged into research activities and also in innovative teaching activities as far as, let's say, global topic related to sustainable development. We will have a module on energy for sure, but also we will have a module on the agro-food chain. We will have a module on cultural heritage as well, and we will have some modules on soft skills like being able to write research proposal, to write research paper, and to do innovative teachings, also taking profit of the expertise that we as Italian university has developed along the last year of the COVID emergency that has forced us to move our in-person teaching to online teaching. So I'm really pleased to be here and to share with you our experience. And I really would love to meet you as soon as possible. Now let's go fast to the presentation. Okay, just disactivate my video. Okay, so let's start with some issue related to energy and sustainable development. We know, I think we are all aware that today there are a lot of interconnection between energy, environment, and society. We know that because we see that in the Agenda 2030, the agenda of the United Nations, we have one goal that is fully dedicated to sustainable development. And why it happens? Because this was not the case with the previous agenda. Because we have recognized over the year that energy is so relevant for the socio-economic development. We will see some further quantitative element later on in the presentation. But also energy is relevant for the quality of life of the people, not only of the society. Energy is also relevant for the global security. If we think to the big discussion about the use of raw materials from oil and gas up to the more modern discussion about the raw materials that are essential for the energy transition in terms of renewable energy, we understand what do we mean. But also energy is relevant for, let's say, assuring environmental protection and preservation. This discussion is quite well placed in the agenda of not only of the United Nations, but also in the agenda of many other organisms. You know that starting from the COP21, that was the conference of the party established in Paris, we had a lot of discussion about the integration or the linkages between energy and environment. But energy is not an end in itself. It's not a final end. Energy is only an instrument. We know that energy is necessary for assuring the availability or the access to services, and then the access of services or resources. And then thanks to this access to resources, then energy is a kind of leverage to sustainable development. One of the most famous nexus that we know, we have already, I think you have already spoken about this, is the Weft Nexus. The link between water, energy, and food is also very fundamental. It's not the only nexus. We have also nexus between energy and climate change. We have a lot of nexuses, but this is probably one of the most significant because we can understand how there is a strong circular link between the availability of energy, the availability of water that is necessary then for assuring a safe and secure food supply chain. So today we are indeed at a kind of, let's say, turning point, because we know that from one side, no sustainable development could be reached without decreasing the overuse of energy resources, especially those who are still related to fossil fuel. We cannot speak about sustainable development if we don't understand how to limit the waste and the pollution that we are creating with the use of energy. And this is one side of the coin, let me say. But the other side of the coin says also, and I think that you are strongly aware of this point, that a sudden shortage of energy could put under threat the societal development. And this is very much true, especially for some, let's say, developing regions or emerging regions. So we know that from the, let's say, from the first perspective, energy and environmental dimension, we know that we cannot further plan our future at a kind of infinite resources. We need to make, the accountability, and we need to be very much aware that resources are somehow limited. And this means that we cannot think that our world is large enough to support whatever use of resources that we aim to do. We are perfectly aware that this is no longer acceptable. And indeed, what is happening at the international level, and I have just mentioned here a couple of elements. They are not, they does not represent the whole set of policies that are around, but just to mention a couple of them. One is related to the national determined commitments. You know that after the Paris Agreement, which was referring to the Conference of the Party 2015 in Paris, then all the countries has committed their voluntary contribution to the climate change. So we are all aware that we have to do our best effort in order to reduce our impact on climate. More recently, and I'm very happy that this was even confirmed despite of the 2020 emergency. So the European Green Deal that aims at making Europe the first carbon neutral continent by 2050 was launched before the COVID pandemic 2020. It was launched at the end of 2019. And we might say that we are really happy that this was confirmed despite of the difficult situation that we are still living today. The commitment toward the European Green Deal was not stopped. And this is quite important because this will be also one of the bases of the recovery. We know that we will be leaving some economic trouble. We are already living some of this trouble today, but we know that we have to come back. We have to recover, trying to change a little bit the trends of the things that we are doing. And I think that one of the most important elements will be to embed all our aspiration in terms of, energy transition, climate preservation into the recovery that we hope soon will be able to start. Energy is very important, is fundamental, as we were saying, for the socioeconomic developments. And we have plotted a couple of pictures that are, let's say, quite relevant for this discussion. The dots are the world countries. They are aggregated into three categories, which are, let's say, high income, high human development, medium human development, and low human development. So blue, low, yellow, high, and let's say this pink, red, very high. So you can see that from this correlation, which associate the gross national income per capita with the total energy supply, how much energy all the country consume, we see that especially in the lower part of the graph, we see that there is quite a very, we could say, linear correlation between the availability of energy and the richness that the country can achieve. We understand also that going a little bit up in this graph, the correlation is more disaggregated, is more sparse, because this is not longer true. If we can compare, for instance, what happened in Europe and what happened in the United States, which mostly they have the similar gross national income, but also the very similar quality of life for the people in both Europe and the US, we understand that they have two different big differences. They have big difference in the energy consumption because the US consume more than twice, 2.5 times what the European consume. So the link between energy and the economic development is very much true in the lower part of the curve, where the energy is really leveraged for the richness, the same richness of the country. Then when we go up, the correlation is no longer so strict, and other issues like behavior of the people, like attention to energy efficiency, can enter the game. On this side, we see again same dot. The bubbles are again the world countries, and we see another link between the primary energy. Sorry for the Italian that stay in the picture, and the Human Development Index, which is the indicator established by the United Nations, which give us an idea of the quality of the life of the people into a country. And we see that this indicator includes yes, a little bit of income per capita, but also indication about how the educational sector is established, or how is in terms of quality, and also how is in terms of quality the health sector of the country. And we see again that for the blue countries, which are the medium human development country, then we see that there is almost a linear correlation that then come up to achieve a sort of asymptotic behavior over the time. So we have a strong link between energy and the economic development, but also energy and the social development of the country that can be represented by the Human Development Index. This discussion led us to say, I'm not a philosopher, I am an engineer, but I did this discussion with a lot of colleagues from this, let's say, with this humanistic background. And they told me that energy, formally speaking, cannot be considered a fundamental right because our dignity is not affected by the lack of energy, but obviously energy is to be considered an instrumental right because we know that without access to energy is very much difficult to be able to guarantee the other, let's say, fundamental rights. So energy, I like to say that energy is our instrumental right because it's a kind of enabler of the achievement, or the enabler for the achievement of the other fundamental rights. But we know that if this were the case, we could say that energy should be given to all. But we know, and I think you also know probably better than me, that this is not the case, because the situation in the world is that we have, in the low-income countries, we have at least 1 billion people not having access to electricity, and we have 2.7 billion people still having access to the so-called traditional use of biomass for their domestic need, with a lot of implication on land degradation, in some cases also deforestation, and last but not least, even in terms of the health of the people, especially when cooking happens indoor. But this is not an issue only for let's say, low-income country. It's an issue also for middle-income countries, where we have at least 1 billion of people having access to electricity, but not having a reliable access to electricity, which means that if we really want to establish, if we really want to develop an industrial sector in that country, is very much difficult because we don't have the reliability of the electricity sector. This means that we could be forced to stop our production for many days over a year, and this put our business under threat. But this is not only a case for low income and middle income. I think this is probably less known to all of you, but even in Europe, in the so-called high income countries, we have, just looking at Europe, we have at least 10% of the population in Europe, which is affected by a problem of fuel poverty. What does it mean? That they have the plugs in their house, they have probably even the heating system, but they cannot afford to pay the bill at the end of the month. And this situation is also getting worse. There are complexity behind. The only cause is not a lack of money, or it's not only an economical problem. There are also structural problems within some countries, especially in the West, in the East Europe. But just to let you know that even in Europe, we have a problem of fuel poverty. The lack of poverty is really, let me say, creating trouble to the people in terms of health, or also in terms of other, let's say, quality of the life. For that reason, for the complexity that we have seen so far, we know that the United Nations decided to put the goal number 7 into the 17 SDGs. And it's quite interesting to see the way in which they have shaped it. The 5 targets are quite, each of them is quite peculiar. For sure, we can immediately understand the first 3. Ensure universal access. This is, let me say, in short term, this is a big challenge for low-income economies, still a big challenge. Increase the share of renewable energy. This is, again, a big challenge that probably developed countries need to keep on working on. the double the rate of improvement in energy efficiency is also a big challenge that probably the most, the countries that are more interested in are the middle income countries. Obviously, 1, 2, and 3, they are general, they are for all the countries, but just to give and to grasp one of the main elements, we can say that there is one challenge accordingly to the aggregation of countries. But what about the other two? Why international cooperation is so relevant, and why also infrastructure and upgrading technology are so relevant? Yes, because we really feel, and I think this was the feeling of the United Nations system, that looking at the energy challenge, we cannot skip to increase the level of international cooperation that need to happen also in a kind of way that promotes knowledge sharing and innovation sharing. And I think that this is also very important for the discussion of what can happen in your country. And also the need of other infrastructure aside of energy is also very relevant, because the place where lack of energy can happen are also places where other lack of infrastructure also happen. Lack of fresh water, lack of healthcare system, and lack of other infrastructure. And I think also this is one of the more important points that come into the Agenda 2063, which is your agenda, the agenda of the African Union. Energy is also important for the Agenda 2063. There is one of the aspirations, in particular the aspiration 2 of the agenda, which is related to the infrastructure, as I was saying, and where the power pools, the continental power pools play an important role. But also there is the very important program for the PIDA, the Program for Infrastructure Development in Africa, which also speak about energy, and speak about energy in a way that should support, not as a final end, but in a way that should support the economic growth and the creation of additional jobs. There are a number of flagship projects into the Agenda 2063, and one of these is related to energy, like the Grand Inga Dam project. We know that even the Department of Infrastructure and Energy of the African Union is doing a lot of job in order to promote energy, the energy transition and access to energy in the continent. So as we can see, the two agendas, even if they are launched by different institutions, they have some common elements that should be that are perfectly in line with the kind of challenge that we have seen. Okay, this was already a complex world. This was already a big challenge that was already big before the COVID pandemic, and we were aware of some issue related to affordability, to the reliability and risk, but also to sustainability, like the big challenges that were behind the sustainable development scenario were mostly let's try to assure universal access, but also let's try to do our energy transition or the development of the energy sector in full compliance with the climate change, without forgetting the other very important part of pollution, which is that of improving air quality. So the challenge was already a challenge before the COVID pandemic. And then we have experienced this kind of shock. All the challenges have been hampered by what has happened. And why I'm saying that? I'm saying that because we have understood during the COVID-19 pandemic, which is still with us today, despite probably all of our hypotheses done 1 year ago, that from one side, the energy sector has really played a vital role in supporting healthcare, in supporting remote working, but also in supporting that minimum of social life that still we are in need to have. Without energy, we could not have been here today together in this kind of action. But on the other side, we see that the economic crisis that is happening along with the stop of many industrial sectors is probably diverting the governmental funds to other, let me say, more direct priority, like healthcare or like the financial support that need to be given to the industry that have been obliged to stop. So we have we understand how relevant is the energy sector, but on the other side, probably we are in a condition to have less investment in the energy sector because money are needed in other, let me say, first priority or top list priority due to the pandemic effect. If we can look at some of the, let me see if I can. Okay. If we can look at together at some of these data, the global energy demand has dropped by 5%. The same drop, a little bit higher, was due to the CO2 emission, but also very important is to understand that energy investment has been dropped down. And this is one important element that we have to consider in order to understand some of the risks that may come out of it. If we look at the situation, the energy demand in terms of percentage was not probably the worst, but during the Second World War, we have a worst decrease in the energy demand. But if we speak in absolute terms, this was really the highest drop ever in the recent history. So what is going to happen? What is the future that we are forecasting so far? It's very difficult. We don't have a single storyline. Our future is still uncertain because if you can imagine some forecast that we did 1 year ago in June last year, and now we are still in the middle of the pandemic effect. So it's really difficult to be able to forecast what is going to happen. But for sure, we have some, let me say, some opportunity that seems to come out. In one of the scenarios developed by the IEA, I don't know if you have already the chance to look at it in the World Energy Outlook 2020, we see that renewable energy, what are the opportunities? I would mention just a couple of them. Renewable energy seems to be the most seems to be the resources that will grow most in all the region. As you can see, the renewable energy are represented by the green bar, the green part of the bar, and you see that in almost all the region we expect to have an increase. This graph represents the difference between what will be in 2030 and the situation in 2019. So it's just a delta, and everything is below the zero. Below the zero, it means a decrease. Everything is above the zero, it means an increase. And also we can see, very important, that the coal use seems to be reduced in many regions like China, Japan, United States, European Union. Only in some countries, in some regions, there will be an increase. So it's important to understand that renewables are set to play a new role, and accordingly to this forecast, the coal use will decline. But what is coming also with the fact that the solar and wind, for instance, will become very important in the electricity production, as you can see here again. The sustainable development scenario, the green bar, seems to give us an idea that wind and solar will really become, let's say, of top relevance for the electricity production. But this will lead the need to do something else, because we know that a further penetration or a massive penetration of renewable energy into the national grid require a lot of flexibility. And a lot of flexibility require investment in the increase in the quality of the national grid. But these investments are today a big question mark, because we know that who is going to do that investment? We know that we need investment. Like in this picture, we see that we need a lot of investment, but we also can see in this picture that, let's say, the revenues from the main grid operator, here we plotted the United States, China, and Germany, has been decreased. So from one side, we will be in the need to make investment, but from the other side, there is, let me say, a risk which we might not have the economic availability to do that investment. And so we see here one of the first risks, which is a kind of techno-economic risk. Technical because we know that the renewable energy penetration call for investment into the national grid, but then big question mark about the economic investment availability. The second risk is an environmental risk, and we know that this is quite a complex consideration that we have to do. First of all, as we can see from this very famous graph, we have to use almost all the technology that that are available. We do not need to be ideological in the position that we have versus technology. We see the role that is played here by efficiency itself, which sometimes is too often forgotten, the role of renewable energy, but also the role of fuel shift and the role of nuclear, of carbon capture and sequestration. But also another important element is that we have to include in our accounting of emission all the emissions that are somehow embedded into the existing infrastructure, and we have to avoid to place or to do some choice today that can lock in a lot of emission into stranded infrastructure. And the last point I want to underline here is that we also need to go beyond the power sector. We know that sometimes our attention is focused on the production itself of electricity, but then we need to look at the role of the end use sector, which means it's very important for us not only to look at the power sector, but to look at the efficient way in which we use energy into the industrial sector. We have to promote efficiency in the industrial sector. We have to promote efficiency in the transportation sector and also in the residential sector. And it's quite interesting to see this yellow part, which appear in the transportation sector, because there will be, we start to see that there will be a role of behavioral change, especially in some specific sector. And the last risk that we want to underline is a kind of social risk. How in line are we as far as a just energy transition? We know that, yes, we need to provide, we need to push the energy transition, but we have to push an energy transition that will be a just energy transition, which means a transition that will not increase further and further the gap between the rich and the poor, whatever they are, individuals, group of people, or the region. We have to push an energy transition that will try to be more equitable at the global level. And we know that, unfortunately, what has happened during the COVID pandemic, some of the most vulnerable, the critical situation is allocated to some of the most vulnerable regions. So we know that the category in each country, the category that are most affected by what has happened are the category who are in critical condition from the economical perspective. But when we look at this problem at the global level, we have seen that the region which are probably experience the more relevant problem with the COVID, with the energy change due to the COVID pandemic are the region that are already developing region, or they are still in the need to develop their energy scenario. And within this scenario, it's very important to understand what will be the role of Africa. For a number of reasons, Africa needs a sustainable energy system in order to boost the economic growth and the quality of the life for the people. But from the other side, the world needs the development of a good energy sector in Africa, because otherwise all our, let's say, climate goal or our sustainable development goals will fail. And last but not least, it's also important to remember that Africa is home to many of the raw materials that are necessary for the energy transition in Europe and beyond. So there will be a crucial role of the continent into these incoming energy scenarios. So this is the complexity. And the complexity is getting more and more complex, and also sometimes is even becoming unpredictable, as it happened in 2020. So how can, what are some of the guidelines we can consider, and how can the science of modeling contribute to these challenges? For sure, we need more and more integrated policies, because we have to understand how energy is connected with the other industrial sector, but also with the development, with the economic development of the country, and with the social effect within the country. We always have to keep an eye on the technological innovation, and we need to be able to model this technological innovation with the progress coming. The citizen behavior is coming to be relevant, and we have to find a way to include also this kind of more social effect into our modeling tool. And also we have not to forget how relevant is the international cooperation on a broad perspective. One kind of premises, which is very relevant for me and for our group, we know that when we go and we try to go into modeling, we know that all models are wrong. That's one very important element we have all to consider. But we know that all these models can be useful. Each model needs to be designed accordingly to the objective that we want to achieve. But it is important that we understand that this is not the reality. The model that we are doing is never the reality. It gives us some hints, some help, some highlights to better predict and to better trace scenarios in order to give proper information to the policymaker. But this is not the reality. That's something I'm doing modeling since when I was PhD students, and I really believe this is something from which each modeler, each scientist doing modeling should remember very much. So having said that, how we are, and I'm coming to the end of my short introduction, how can in our group approach the needs that we have seen are coming out from the energy challenge? We were energy modeling until a few years ago. Then we have understood that due to the complexity of the energy sector, we need to use a multi-layer integrated modeling, which has basically, is a little bit more complex, but just to explain shortly, it has basically 3 layers. We can't avoid to have a bottom-up technology models, which give us the detailed productive system characterization. And this will require knowledge of thermodynamics, stochastic system dynamics, and many others. Then we have a layer, and in this layer, we, let's say, detail the different technologies. Then in an upper layer, we put all this technology together, just say it briefly, in order to create the energy system. In the first layer, we have the characterization of the solar panel, of the combined cycle power plant, of all the technology. Then in the second layer, and also we characterize the demand, as we are going to see in a while. In the second layer, we put all of them together and they create the energy system, the energy sector for that specific country. And in the third layer, we try to link the energy sector to the mesoeconomic sector of the country, which means that energy, as we have just said, is relevant because it feeds the transportation sector, it feeds the industrial sector, it provides energy to the residential sector. And so it's important, if we really want to understand the impact of a certain energy scenario, to understand how this scenario interacts with the rest of the economy. So we have these 3 layers that I'm trying to deepen a little bit, but just shortly. The first one requires a lot of knowledge on the technological development, on the characterization of the specific technology. We can model components, processes, and also products within a specific supply chain. This means that in this way, we are able to add slowly, or fast, it depends, each new technologies that may come to be an opportunity. We are not stuck to use all the technology. Then in this layer, we also try to detail the energy demand. And we try to detail the energy demand by using a bottom-up approach, which tries sometimes also to include behavioral effects, because we know that the demand may change according to the change in the perspective of the people, the behavioral change. So, for instance, what will happen after the COVID pandemic in terms of transportation? Once we will be able to be back without the lockdown, are we going to use transport in the same ways as we did before, or there will be any changing in the people behavior? So we try to, let's say, to include all these elements of social behavior by approaching let's say the creation of the demand using, for instance, some socioeconomic dynamics tool. The second layer is the layer in which we put all the technology together. We use the demand that we have developed in order to, let's say, simulate, but also in order to do planning for the energy system. And we have 2 we mostly use two different approaches. One is more related to, let's say, mesoscale multi-energy system modeling like microgrid SPI, which give us an opportunity to make a linear optimization or a mixed integer optimization of microgrids thought for off-grid solution. And the other approach, which is not that different, is using Calliope or osmosis. I think probably osmosis has been already introduced to you in order to optimize whatever it is, the dispatch or the capacity expansion of a national energy system. And we have tools that give us the optimal or the near optimal alternatives, which means not only alternatives based on the least cost, but alternative based on an ensemble of criteria that might be of relevance for policymakers. And the last layer is the layer in which we say, okay, once I have designed the energy sector given a certain perspective, then I want to see how this is impacting the rest of the economy, the industrial sector. If I have this system with this energy mix, now what does it mean if the industrial sector use this kind of energy? What are the implications? What are the impact in terms that we are able to measure in terms of environmental impact, use of resources, overall emission, embedded emission, not only direct emission, use of water, for instance, because there are some energy solutions that are more water demanding or more land demanding. And so we are able to have an overall environmental impact, not only in terms of, let me say, CO2 emission or pollutant emission. And we are also able to evaluate, let's say, other kind of impact, like the economic impact, the added value that is brought into the sector, as well as job creation that might be come with that development. So in this way, we try to integrate our, let's say, deep technical engineering-based knowledge with a more broad knowledge, which try to give the impact over the whole economy in terms of environmental parameters and in terms of economic parameters. Try to answer to what were the 4 points that we have already underlined. And in this way, we are also able to see the impact of our, let's say, technological development, energy modeling on the sustainable development goals. I have almost closed my presentation, and I leave you with this very nice stance by Einstein, which is a kind of driving force for our modeling efforts, which try to push us every day a little bit further. We know that we cannot solve a problem by using the same kind of thinking we have used when we created it. So aside of the Agenda 2030 being a transformative agenda, in that transformative part, we also see that there is a transformation of research. And we think that more multidisciplinary research is needed if we really want to tackle the big challenges that are, let's say, at the door of the cities of mankind. And I thank you very much for your attention. Arnaud?
Yeah, thank you very much, Emanuela. I'll let your colleagues maybe take the floor from now on the next piece of presentation, unless you want to take some questions now. Really up to you to see how you want to interact with participants. But thanks for this first very great and inspiring introduction.
Okay, thank you. If there are, maybe Francesco can support me if there are some questions coming up.
Right now, there are no questions.
Okay. At any rate, dear colleagues, it would be for me a big pleasure if you have further discussion that you want to deal, and we confirm our availability in case the colleagues want to have further discussion. Now I give the floor to Nicolas.
Okay, so I'll share my PowerPoint.
Sorry, Nicolas, maybe before you start, one question came.
Okay.
I'm reading it. Which model is more relevant to calculate emission reductions?
Sorry, can you say it again? Because I cannot see.
Which model is more relevant to calculate emissions reduction?
This is a very nice and interesting question. It's always when I teach to my students, I always say it depends, because it really depends on what is your goal. If your goal is to calculate direct emission, I mean the emission that you are bringing, let's say in the place where, for instance, you install your power plant or whatever is your technology, then you can even avoid to use any complex modeling tool, because you can make direct calculation accordingly to the fossil fuel that you are using, and then you can make a straight calculation. But when you come to understand, and I think that Nicolò Golinucci will give you example on this later on, when you want to understand how much is the sorry, not how much, but how we can have an overall global level emission reduction, that you need to know many things, and you need to know also the trade that are traded between regions, because each time I import a goods or whatever other things, I don't know, I'm importing my my laptop or my whatever device, I'm also bringing with me some CO2 emission that are emitted somewhere. This is the so-called approach to the embedded emission. And if we really want at the global level to reduce emission, we need to know that calculation. We need to make that specific accounting. Otherwise, we are only looking at the emission that are directly emitted in a place. But if we work as mankind, we need to be aware of the overall embedded emission. And this is the principle based on which policy should be driven. But I let Nicolò Golinucci later on to complement this answer.
Okay, thank you very much, Emanuela. Unless there are more questions, maybe we can shift to the presentation by Nicolò. Thank you, Emanuela.
Thank you. Bye-bye.
Okay, so shall I share my screen now? Okay, perfect. Okay, great. So, good morning, everybody. My name is Nicolò Stevanato, and as Emanuela already introduced me, I am a research fellow here in the SESAM research group at Politecnico di Milano. And today I'm gonna give you a brief overview on the energy modeling methodologies and approaches we use in the group, in particular for addressing the issue of access to electricity. So I will start with a brief overview of the matter that you might already know pretty well. But as you know, the issue of planning electricity access strategies is particularly complex in rural areas where the population is scattered and the levels of electricity demand are low. And these two characteristics together make the technological solution of extension of the national grid economically and technically unfeasible or unsustainable. For this reason, other technological options have been developed and are now in use as alternatives to the national grid for bringing access to electricity. These other technologies are the so-called standalone technology, that is, can be a single source of energy, that might be a PV panel or a standalone diesel generator that serves one single user, might it be a household, or in other cases can be an entire school or health center, but is characterized by being only one source of energy and serving only one user. particularly suitable when the population is very scattered. That this does not justify bigger systems for the area. In cases we have a little more dense population, and the energy demand starts to be higher, and we also start to take into consideration, for example, productive uses of energy. The solution that comes to hand is the mini grid or microgrid. Microgrids can be characterized by different sources of energy in the same system. Might it be PV panel systems plus a battery backup energy system and a diesel generator, for example, but can be integrated with hydropower, with wind turbines, has a capacity that is usually below 500 kilowatts, and it's starting to be a common technology used for granting access to electricity. The third option is the common national grid that is extended up to the areas that we want to bring energy to. In order to develop strategies for deploying such technologies, energy modeling comes as a useful and scientific-based help. There are different categories of models, and today I'm going to focus in particular on energy system models for sizing off-grid systems. Starting from where Manuela left us, my presentation will focus mainly on layer 1 and layer 2 of the methodology of the SESAM group, because I will deal mainly with characterization of technologies, of demand, supply and demand, and the optimization of the energy system that makes use of such supply technology to satisfy the assessed demand of the area. But first of all, let's make a brief recap. Probably you already have been through it, but I would like to make some important points. What is energy modeling? Energy modeling is the mathematical representation of an energy system in order to make simulations and assess the impacts of actions and policies to the represented energy system. Energy model can arrange a very wide range of temporal resolutions and geographical resolutions. Depending on the problem we are facing, we choose the proper energy model. So there is a wide variety of energy models, and depending on the kind of problem I'm facing, the solution I'm looking for, I select one or another energy model. In particular, today we are going to focus on supply generation and optimal dispatch models. So the output I'm looking for is the optimal sizing of supply technologies and the optimal dispatch of such technologies. A typical, let's say, a basic energy system model take as input the demand I want to satisfy. So what do I need this system for? The available renewable energy sources in the area in order to be able to properly size the technologies, the characteristics of the technologies involved, so I know how they will behave, what are their costs, operational and maintenance costs, investment costs, and all the parameters of my project. So how many years will this technology be used for, and what is my economical context. As an output from such kind of models, I expect the number of pieces of technology I have to install, so optimal capacity, how to properly use them, so optimal dispatch strategy, and the costs I'm realistically going to face, investment cost and operation cost, and as a result, the levelized cost of energy of the system. When I build an energy model, This showing here is an example for a national, so in an entire country or a region energy system. I assess the existing resources for energy generation. I understand how in my considered system such resources are transformed into electric energy. The electric energy is then passed on to the transmission system and to the distribution system. The model can be multi-regional, so I can even assess how the region that I'm seeing interacts with other regions by selling and buying electricity to other regions or other countries. But the final goal is always satisfying the demand of every region I'm considering. So this is how I build the model. But what's behind this curtain of energy modeling? Well, it's usually when we talk about optimization, it's the satisfaction of an objective function that is usually minimizing the overall costs of my system. So I'm looking for the economically optimal solution to my problem. But all my system is constrained to physical boundaries of the real system I'm representing. Such boundaries are the energy balance, the power balance, mass balance, because I need to be consistent with the physics of the problem. I have technological constraints. A PV panel will behave in a certain way. A diesel generator will produce energy according to its efficiency to the kind of fuel I'm providing. Then I can consider market constraints. So the more economical source of electricity will have the priority above the others, and economical constraints. So what are the costs of my technologies? And in the end, I'm looking for the most economical, for the cheaper solution among all the existing solutions. What do I mean when I say all the existing solutions? Because optimization is finding the minimum or the maximum, because it's minimizing or optimizing a function or maximizing a function. Let's make a very simple example. I want to maximize x plus y, and I subject this my entire range of solutions to a series of boundaries. So x has to be less than 3, y has to be less than 4, x plus 2y has to be greater than 2. So these that I just listed are simple representations of the constraints I was talking about. So when I take all my constraints, I define my feasible regions. All the solutions inside this area are feasible, can actually work and satisfy my problem. But then which one is the optimal? So which one is maximizing, in this case, my objective function? Well, there is a theorem, the Simplex algorithm, that says that if I follow the borders of my feasible solution area, I will eventually reach my optimal solution, no matter which direction I'm following. This is called linear optimization, and is at the base of every model we make use of in our research group. Now, this is not fundamental, but it was to give you an idea of the mathematics behind an energy model. I have a problem, I make a mathematical representation of the physical model, and through linear optimization, I identify among all the feasible solutions the best one. This is the same example of the Simplex algorithm, but I'm going n-dimensional, because of course all my physical problems consider several dimensions. But now let's go to have an overview of the existing and most famous models. We basically have two categories of models. We have the so-called commercial models, Markle times Homer, Message, Leap, that are the most used by international agencies and are commercial models. On the other side, there are the open source models that are the one we make use of in our research group. They are more suitable for research purposes because they are completely adjustable to the needs of the modeler. And the source code of the model is completely open to anybody to see. So anybody can freely download the model, open the model and see which equations are governing the model, and can even change them according to the needs of the user. But let's jump a bit more into off-grid energy system modeling. That is the thing I would like to explore more today.
Nicolo, sorry for interrupting. Maybe there is one question that might relate to the slide you just had on a different type of energy modeling tools before you deep dive into the off-grid. Maybe if you want to take it now.
Okay, I think I will take into account this. I will answer to this question in the next slides, because of course resource assessment is relevant. It's true. But I have dedicated some slides in the next slides. Thank you. Could you please give us more explanation on power and mass balances as part of the modeling? Sure. When we are building, let's go here. When we are building an energy model, I have to ensure the physical nature of the problem I'm representing. Meaning that if I'm representing a system, it can be an entire nation, or it can be just a village, a rural village. Let's take the case of a village now, because we are talking off-grid energy system modeling. All the energy, I have to ensure that all the energy that enters the system equals the energy that exits the system. So if I have a certain amount of sun radiation and a certain amount of wind power that enters the system through these two technologies, then at the net of the efficiency of all the technologies, so losses that are a way for energy to exit the system, then it has to balance out with the energy that exits the system, that is the load. So I'm basically just saying whatever enters the system exits the system. It's a balance between supply and demand. It's just that. We say energy when we talk about the overall annual energy, and power when we are considering instantaneous or time step specific energy. So basically this question helped me to enter the new subject. When we say that we optimize an energy system, an off-grid energy system, what we do is considering which technologies do we have available. That can be supply technologies, also fossil fuel supply technologies for backup, storage technologies, battery banks, for example, and a load that I have to satisfy. Now, knowing the costs, both variable and fixed costs, investment costs, and available resources, that I will then explain a bit how we deal with the definition of available resources. And I have the load demand that I have to satisfy. My optimization provides, among all the feasible solutions of this problem, which one is the optimal one in terms of size of, for example, PV, size of battery, genset size, and how much fuel I'm going to consume. Okay, so I have as an output the optimal size of all the considered technologies and the optimal dispatch strategy in order to satisfy my load with the available technologies and resources at the best, in the best way, in the most economical way in this case, because the objective function is minimizing the cost, the overall cost. But all these processes are around needs of people. We do not optimize technology because we like to bring kilowatts to rural areas. We do it because there are needs of people, of populations, that has to be identified and properly satisfied. So our entire process of modeling is always based on a very strong stakeholder engagement and needs identification together with the stakeholders, with the population of the village and the most relevant authorities of the country and of the specific village. Together with them, we formulate scenarios of future demand, existing demand. We try to understand which technologies are more suitable for that particular context. Then, together with the knowledge of the locally available resources, there are several ways to assess locally available resources, both models online provided by, for example, by NASA or other institutions, or you can even meter, register, measure the amount of available resources through instruments on the ground. We combine such information and we make the optimization of the system. But everything starts with engagement with the population. I see a couple of questions. When you refer to energy modeling, do you consider electrical energy only? No. Thank you for the question. Great question. We also consider in some of our studies thermal energy or energy for cooking. I will get to it in the examples. Thank you. Seems mic is muted. No, I think my mic is open, but I ask Arnaud if you can hear me.
Yeah, we can hear you very well, at least for me.
Okay. Okay, so as I just said, the sizing of the system is driven by the demand. And the demand is evaluated based on needs of the community. It's not assigned a priori. We deal with communities, we engage with them and understand what are the needs. We satisfy needs, not electricity amounts. Access to electricity is then just a mean to get to development. Through access to electricity, we aim at unleashing development chains. And through our models, we help policymakers and international agencies to to develop electrification strategies, policies, or even single projects. Okay, but as has already been asked, how do you assess the load demand? How do you assess the available renewable resources in an area? Because yes, okay, I explained what is the logic of an energy model, but how do we provide the inputs? Or what do you do once you have the optimal capacity? This is not just a number. Once you have the optimal capacity, then you have to do something with that. Well, we have developed a strategy that is the so-called comprehensive energy access planning that gives a kind of guidelines for deriving my inputs and properly using my outputs. So as I stressed already, mathematical optimization is not enough. Modeling rural access to electricity needs to follow a path built around energy and needs of people. Mathematical optimization is just a step inside a procedure made of many steps that now we are going to see a bit. The comprehensive energy solution planning aims at seeing exactly this. I see a question. What are the bases to design of grid energy model? Let's see if these steps help you understand what are the bases to design energy system model. If I did not answer, then you can ask the question again, specifying what you're still missing as information. Okay, first, as I already stressed, we focus on priorities, identification of needs. So we do not care about the number of kilowatts, but we assess the needs that can be from basic needs such as lighting up to more complex or more complex, we can say, needs such as productive uses of electricity. So there are business that can be developed thanks to electricity or thanks to energy, and of course societal needs, so education, healthcare. Then we transform such needs into kilowatts. Alongside with that, the second input is the assessment of available resources. How we do that? We rely on global models, such as as I said, NASA models, that give us an idea of available resources through many years of recorded data of availability of resources and model future availability of resources. And we couple that with on-the-field evaluation of existing resources. So if there is the presence of a river, then I will realistically favor the building of an hydropower small plant for the mini grid, even though, for example, in the entire sub-Saharan Africa, the sun resource is very abundant. In the case I have a river, then it makes much more sense to use a small hydropower production system. Once I have identified the needs and the available resources, I also have to identify the proper solution, because one solution does not fit all. Need for proper strategy is important. So I identify, based on the specific situation, which kind of technology is the most suitable. So the standalone technology, a mini grid technology, or is better to extend the grid. Once I have identified my most suitable technology, and let's say we have identified the mini grid, then I perform the mathematical optimization I already presented to you, and I obtain as an output, based on the needs, the technological optimal solution for the various options that I had considered. Size of each technology and how to properly pose them on the ground. Then it's not over, because now I have just numbers that tell me what is the right sizing of the technologies involved. With that, I can start to develop proper business models to deploy the proper ancillary activities. We have understood through the years of research that energy itself is not sufficient to unleash development. We also need to provide ancillary services to the community, for example, access to microcredit or help to develop income generating activities. So all the other activities, together with the technology for access to electricity itself, that will foster development in the area. Once I have identified the proper system sizing in all terms, I evaluate the supposed impact of my project and ask myself, did I address all the needs that I had identified? This is kind of the process that we have developed for proper energy system, energy access planning. So it's not just technology. Technology is one step in a bigger framework. But let's see three cases, yes, 3 examples of local mini-grid optimization that we have carried out throughout the years. This is El Espino, a small village in rural Bolivia. We have performed the Adoro field campaign through surveys and engagement with the local population. We understood the needs and what were realistically going to be the future needs of the population in the next 5 to 10 years. And we, in this case, for example, we also considered energy for cooking, because we wanted to make a more comprehensive, let's say, not only electricity. Well, it was electricity as well, because we considered electric cooking. So we asked ourselves, what would happen if also the electric cooking technology might start to enter the village? How would the system react? So we developed a stochastic solution. It means we took in consideration different possible futures and developed a solution that was the optimal one for a range of possible futures. Some of these futures considered also a small penetration of electric cooking in the village. And these are, for example, the different load curves that were consequent to the different possible scenarios that we have developed together with the population. Secondly, another example that we have carried out was, okay, now I am able to assess different futures, but what if I'm able to assess how the load increases throughout the years? And we developed a methodology to take into account in our mini-grid sizing, not only the future demand, but the evolution of the demand from today to 20 years from today. And we observed how taking into consideration such evolution of the demand helps the mini-grid deployer to drastically reduce the investment cost in the first year, because you can plan to deploy a part of the technology in the years later, avoiding all the cost of the technology in the year zero. Finally, another example was the design of not just mini grid, so only electricity, but the sizing of a multi-energy system. We took into consideration also domestic hot water, and we explored the possibility to make PV panels and solar collectors interact in a single system and make the two systems communicate one with each other. And we saw how designing an integrated multi-energy system brought us to more than half price in terms of net present cost compared to the traditional energy system or even to the conventional microgrid. So exploring the possibility of making an interaction, an integrated multi-energy system between electricity and other kinds of energy needs brought to a much more optimal solution that was not reachable, not available if we considered only standard conventional microgrid solution. So these are some examples to give you an idea of what we were able to do with the tools in our hands. And the fact that the tools were open source helped us modify them in order to take into consideration evolution of the load or add the thermal system to the microgrid, because we were capable of playing with the tool and modifying what we needed. These are just some references for you if you want to take a look at what I just said. And that was everything from my side. I hope everything was clear and also interesting. I'm here for questions if you need, if you are interested in something more or you want me to explain a bit better some parts or some. I see you can raise your hands as well. We can engage in some discussion now. Feel free.
Yes, maybe the question on the muted mic was on one participant saying that he was not able to speak. So if that is the case, you just need to raise your hand and we can allow you to speak.
Ah, okay.
Maybe, Nicolo, one quick question from me on the last slide you were showing. Can you just detail a bit what the integrated multi-energy system includes in terms of, I can see there is different type of electricity generation, but also other equipments to capture energy, storage. Can you describe a bit more the entire ecosystem?
Okay, yes, thank you for the question. What we did was understanding that electricity is just one of the different energy needs of a community. So we wanted to explore the possibility to take into consideration different energy needs and see how the integration of the two systems that are usually separated. So I have a boiler for my hot water and I have a generator for my electricity. But what if I make the two systems interact? So here you can say how we have the standard mini-grid in black, PV, battery bank, diesel generator, the electric load, so my need for electricity. But on the other hand, I have solar collectors, the one you can see here, and Lpg boilers, so the standard boilers for domestic hot water. Solar collectors make use of a tank for storing hot energy. But what if I put inside this tank a resistance, an electric resistance, that can be powered by the electric system? So in this way, if I have abundance of, for example, electric energy, I can store part of my energy in form of hot water instead of battery bank, and then use during the night the extra energy that I have stored in form of hot water or in terms of battery bank also during the night, saving gas from the boiler. So it was interaction between the standard mini-grid and what is usually the domestic hot water system. And we observed how this interaction between the two systems allowed for further more optimal solutions compared to the standard approach. I see there are now a couple of questions. Why we choose stochastic models? Okay. Still, I'm not clear on mass balance. Okay. Stochastic model first. Let me see how we can do it. Stochastic models is just a way to take into consideration uncertainty, because when we model future scenarios, future evolutions of demand, we do not know what is going to happen. So we might fall in the risk of sizing a system for a particular scenario or future that I think is the most probable, but then I could find myself in another situation and my system that I have just sized is not optimal or even dangerously wrong for that new situation I found myself in and I did not foresee. Through stochastic optimization, I can say, okay, I'm not looking for the perfect solution for just one case, but I will take into consideration different possible futures and design a system that will behave in the best way possible for all of them. So it's not the best for just one, but it's the best way I can deal with whatever situation I'm going to face. So it's a way to be ready for uncertainties. I hope this answered the question. Feel free to ask again if you didn't, if I wasn't clear enough. Still, I'm not clear on mass balance. It's a matter of being consistent with the physics. If I am modeling a dam, an hydropower dam, then I have to characterize my model in terms of the water that is entering the dam is then also exiting the dam. I cannot have water that disappears or appears because we are building mathematical models. Mathematics do not know what water is. You have to be very careful in describing the entire physical situation in order to for the model to behave as much as possible similarly to the real physical system that you are trying to represent. You will never be able to get something that behaves in the same way, but you have to try to consider as much constraints as possible to simulate the real behavior of the system you're considering. How do you derive the scenario tree based on what? Usually we derive scenario trees based on engagement with the local population and stakeholders. So for example, we engage with the local rural electricity agency, we engage with the mayor of the village and with the selected part of the population, if not all the population, and we try with them to understand what the possible futures are. And we also look at similar situations that already have been through a similar process to see how in history other situations similar to that evolved in order to have an idea of the range of possibilities. The type of energy we use, has it any factor? The type of energy we use, has it any factor on design of the model? Could you detail a bit more this question? I'm not sure I understood completely what you mean by that. And how about the dynamics of the system? Do you consider it in your model? In the case of the multi-year, yes. We considered a dynamic evolution of the load. So we consider 20 years and every single hour throughout the 20 years with the dynamic evolution of the load and the possibility to invest in different moments of my project. So as you can see from here, I have these 4 scenarios. Okay, scenario 4 is the case when I invest in different moments. Okay, my model can decide to delay the installation of a part of the technology to future moments. So in this case, it's dynamic. In other case, we just are static over 1 year, for example, and we size a system over the supposed energy consumption of a year and then project it to 20 years. So we do both, depending on the needs, on the situation we are facing. Can you share something about LEAP? I have to say I'm no expert on LEAP. I have never used it. I know it's a very, very fledged model. A lot of agencies and researchers make use of it. It's particularly suitable for very big geographical resolutions. So you can consider entire continents, if not the entire global situation with LEAP. And it's designed for very long-term scenarios, up to 50 years of scenarios. But it's not my expertise, the LEAP model. I can suggest for sure some literature to deepen the knowledge on LEAP. I can pass to Arnaud some references and he will share them. Also here, you already have an idea of some of the references I used to build this presentation.
Okay, so unless there are more questions, maybe we can move to the next part. Just a word to you all participants. Given that we started late, and again, sorry for the technical issue, and given that you are having many questions, I am anticipating we might run a bit late. So I'm not sure we can close at 12:30 for your lunch break. So I hope you can take a few more minutes, and maybe we can aim to end at 12:45 or just a bit later, so that we have time to hear from all the very interesting presentation from Politecnico di Milano colleagues.
Okay, so for the moment I will. Arnaud, do you want to make a break or is it too late?
I advise we directly can move to the next one or to the next part. I don't know if it's you or the other Nicolo who takes from here.
Yeah, I will take from here.
Okay.
So I start to share the screen. So we start as soon as possible. Tell me when you can see the screen, please.
Yeah, all good. Not yet in presenter view, in large display.
Okay. Now should be in presenter view.
Yeah, that's perfect.
Okay, great. Let's start. So we are now at the third block of our presentation. So we had an introduction by Professor Colombo. Now my colleague talk about the first 2 levels of the framework that we are describing, which is actually how we work in our research group. And with my presentation, we are going to talk about layer 3. So the layer that is also considering mesoeconomic activities. What does it mean? Are we going to talk about models that are able to take into account also socioeconomic aspects and how different sectors interact with all the other sectors, and in particular with the energy sector, since we are here for talking about energy modeling. I'm going to try to give an end-to-end presentation of the ideas that were behind the research, the main research that I have delivered so far in my PhD career, starting from the problem of carbon emission reduction. We already had some questions in the chat about this, so we're going to deepen in particular this topic, starting from the problem. So why do we need to reduce emission? And then moving to how industrial ecology, that as we are going to see, will be the main scientific field behind all the reasoning, can help us in dealing with such a problem. And then we will go in details talking about one of the methodologies within industrial ecology that was employed in the particular work that we run into. So let's start, starting from carbon emission reduction. We refer to this as the hottest sustainability challenge. We know that there is an SDGs related to this, and that European Union very recently started having a very important, let's say, effort in dealing with this SDG. But very recently, actually, other countries are joining the challenges. And in particular, we had Japan, we have South Korea, and recently also China, which, as we know, is very important from the point of view of the share of total emissions that are produced within China's boundaries. These are just some Google research just to provide the context of the urgency of this particular challenge. But a question may arise: why so relevant? Why we are supposed to reduce carbon emission? Here I reported a very nice dashboard that you can Google and you can find at the link that is here described. And that is basically trying to put together all the scientific studies that were developed and published related to a field of science that is called attributional extreme events. That basically is trying to asking and answering the questions related to how important are the part that of CO2 in atmosphere that were released from human activities. Actually, this is very hard to be done. That's why there is a whole scientific field related to this. But more or less, we can we may say that there are an increase in the frequency and in the intensity of these events in some cases on these studies. So the main reason why we are so concerned with emissions is that on the long term, we are expecting some drawbacks, some damages. But let's try to provide the magnitude of the problem that we are trying to resolve. And what happened on the last year actually is something that we didn't have so far, and that can help us giving exactly the idea of the effort that we are trying to make. If you consider that, at least this is data are taken from this publication that now maybe is can be updated, and we are going to see the updated values of this. But more or less, we can say that in 2020 we had a reduction of CO2 emission, actually of greenhouse gases emissions, of around 4.5. That is more or less the reduction that we should have every year if we want to meet the 1.5 emission reduction goal. So the pathway that according to climate models should bring us to just an increase of 1.5 degrees in 2030. 2050, sorry. And from the other side, so we had this, that it was basically was something that came out of a pandemic situation. But from the other side, we also had a reduction in GDP, and we try to assess this reduction, and is more or less equivalent to a reduction of GDP of around the size of German economy. This is just to give an idea. But as we are going to see, these are not the only way to reduce emission. This is something that occurred, and we have seen a reduction. But this is, again, helping in having an idea of the numbers around. Actually, we have an update in these values, as are we going to see, and I also see already that Arnaud is providing updated data on this. Yeah, here I'm presenting the data from a website that is monitoring CO2 emission live, let's say, and here you can see the difference from year to year. And here I'm talking about a reduction of 4% because actually we are not considering, emission from international aviation. So these are just taking into account the emission that took place in different regions. But from the GDP point of view, actually, we were more pessimistic during 2020, and the reduction is actually less than the one reported in the previous study. Now IMF is, as always, updating these values in terms of projection and estimates. But in general, as we can see, there is a lot of difference in GDP reductions. That depends on geography and again also on estimates, but this is the main reason. And again, this is the link to the website. Once we share the material, you can have access. And yeah, here I'm just reporting what the difference that is reported is actually related to international aviation. So 4% without considering international aviation, and more or less, if I remember well, very close to the number that Arnaud is reporting in the chat. So for 5.5, more or less. And yeah, actually these are numbers that are still in updated, in update, let's say. So we have seen what could happen only considering the changing consumption patterns. Actually, we had a reduction that is due to, again, something that was exogenous, but actually we think in general, as engineers, that there are many other ways to reduce emission. And actually we should think about changing technology for reducing emissions. I see a raised hand, so I maybe take the opportunity to give the floor to Asefa. So please, Asefa, if you have something to say on this, I think you should unmute yourself. Okay, I cannot hear you, Asefa, but maybe we can have some other occasion later on. So coming back to the presentation, so we have seen this change, but actually, as I was saying, there is the role of carbon intensity. What is carbon intensity? Probably you already know, but just to remind you, basically, we are talking about the ratio between the CO2 emission of a certain jurisdiction divided by the production of that jurisdiction or economy more in general. And basically, we usually measure production through an indicator, very famous indicator, which is GDP. And so if we take this into account, we see a reduction that is taking place more or less all over different countries. In particular, again, I'm talking again about China because of its relevance in this problem, but as we can see, they reduced a lot their carbon intensity, but probably this is mainly to an increase of the denominator in this ratio. While actually in country like our country, Italy in this case, the reduction is more or less related to a reduction of the numerator. And so these are just to give you an idea of how you can change your carbon intensity through economic ways, let's say. But the main message that I want to bring here is that technological change is not a spontaneous, it's not something spontaneous. As we are going to see, there are some other effects that are bringing the change in the technology. In particular, I are summing up three main mechanisms that are actually interlinked one with each other, but basically we have demand, investment, and policies that are playing a role in pushing technological change. And here I'm reporting some data from Bloomberg and EF that are reporting how quickly technology, very important technology for decarbonization, such as lithium-ion battery packs, decreased the cost for one single pack in only 10 years. We're talking about a reduction, maybe you cannot see it very well, of 90% in 10 years. But what's the force behind this reduction is probably a very important increase in demand in the future. That is, again, bring by also policy, because this is going to be the case when we are going to move, as it seems, towards in the developed, let's say in the European and the USA, by moving to electric vehicles. But again, just to give another example, which is related directly to electricity production, there are also very important learning by doing effects that can be observed in the electricity sector. Let's see the photovoltaic. The photovoltaic, we had a lot of time using photovoltaic only for niche applications such as spaceships. But thanks to political will and financial will to move and update the electricity system, we are now seeing a very important learning course. And in particular for photovoltaic, this is very, very steep. This is taken from a divulgative article from our working data that is reporting scientific evidence for this decrease. So we have seen the carbon emission reduction problem, different strategies related to technology and economic patterns. And industrial ecology, it's actually the science that we are going to put on the table to try to address this issue. But what is industrial ecology? Industrial ecology is the science that studies socioeconomic metabolism. In general, we are talking about industrial ecology when we are referring about the interaction between the so-called social sphere of causation, where we all as humans, we are taking a role. So we have our needs that are usually met in what we call markets. So where the demand and the supply are meet together and determining also the prices that can influence our behavior. So there's a lot of complexity taking place in the social sphere of causation. From the other side, also the biophysical sphere of causation is influenced by very difficult mechanisms and that are related to natural environment. And in particular, in this specific problem, the place where we should put the attention is on the frontier between these two spheres that are actually overlapping one with each other. In particular, we have from one side the human activities that are using natural resources, and from the other side we have things like emission that can have an impact in terms of pollution on human health, or in the longer term on change in climate patterns. So the idea is that if we have an interaction between economy and nature, maybe we can find a link between those two. And in particular, we used to talk about carbon taxes, and we're going to see what we are referring to. But the first point that I want to make is that if we ask economists, we find a lot of agreement in the usefulness of carbon taxes. Most of the economists agree that it would be a good idea to address the problem of reduction of emission. But okay, let's put the price on carbon. We see that is a good idea. But what is the fair price of carbon? And we talk about fair price of carbon by terms of social cost of carbon also. And we were going to see that that may depend on many things. But let's, again, start from an idea of the tons. This is actually something more referred to the behavior of Europeans, these 6 tons of CO2 per capita every year. But when we are talking about a ton of CO2, we are referring to this. And the value, the cost behind the release of this ton of CO2 may depend on many things. It depends on the shared socioeconomic pathways. So basically, how demography and economic growth can influence the future emissions. From the other side, also the concentration pathway. So with the same level of development in terms of economy and demography, how can we have an impact on the carbon intensity? So having the same with less emission. And also it depends a lot on the damage function that we assume. Not only this, also on discount assume. So basically how we value time. So how important it is to have a damage today or a damage in 10 years, for example. This is very important, also very difficult to understand and determine. And also that depends a lot on countries. Basically because different countries can have different expected effects in the future, but also different needs today, okay? There are also many other things that are influencing this. And I'm here reporting a very nice infographic that you can find in the link here again in the slide, that is going to show you a little bit this concept. So if you change the projection of GDP and demography, how can this impact on the social cost of carbon? And again, considering that some places may also have actually some benefits out of increase in emission of CO2, because there are some places that are very cold now and probably you cannot live there. But maybe with higher temperature, this can change. But again, the point is that there is a lot of uncertainty beyond this, and we should always consider this. So the problem is very complex. But we actually did something on this already. We already put a price on carbon in many places in the world. Here I'm reporting a dashboard from the World Bank that is reporting the main 2 different mechanisms for pricing carbon in different jurisdictions. From one side, we have the carbon tax. So very easy, we put a price on carbon. We are targeting the emission price, basically. And ideally, we would like to have a price of this carbon that is the social cost of carbon, ideally, if we can determine precisely the social cost of carbon. From the other side, well, sorry, I give just an example because Sweden was the first country that introduced a carbon tax. Now is also the country with the highest carbon tax of around 110 euros per ton. Then the other approach that you can have, that actually Europe is sharing right now, is the ETS. So the ETS is, the idea behind the ETS is that you have a maximum amount of CO2 that you can release within a certain time step. And so you will give allowances to the players in the economy as far as the total amount of CO2 is under a certain threshold. So in this case, we are targeting emission volumes, not emission price. Well, this is an indirect effect, but we will see this. And ideally, this would work perfectly if we have a perfect competitive market. We know it's not the case, but ideally, if all the agents of the economy have a perfect information, this could work very efficiently. In Europe, right now we have a DTS, and now the price of the allowance that, as I was saying, is not directly imposed, but is an effect of an equilibrium in the market, is around 40 euro per ton. Again, talking about China, since you see this is in green, this is actually very recent. The ETS in China took place in 2021, very, very recently. This is actually going to be updated probably in the very close future. But let's have a look at the first emission trading scheme, because this is going to be connected with the key study that I'm going to show you, which is the European one. And let's see some drawbacks that are behind. Basically, for many years, we in Europe had a very low price of CO2. These very low prices took place from more or less the beginning of the scheme up to 2018. Only very recently, we have seen an increase in the price. And this actually had an impact on the response of the European countries. As you can see, here I'm reporting a chart from the European Environmental Agency and reporting Germany, United Kingdom, Poland, and Italy. And you can see the total production of terawatt hours of electricity by year and by technology. Maybe you would notice that there are no very important decrease in CO2 emission, which is the black line. But there is an exception, which is United Kingdom. As you can see, the decrease is steeper. And so the point is that low ETS price didn't have significant impact on the reduction of CO2 within these years, as you can see. But actually something happened in 2013 in UK. And this is the so-called carbon floor. So there was the possibility to introduce a minimum price of CO2. That was an important signal to UK's investors on power plants. And this actually amounted on more or less 19 euro per ton of CO2. And I don't know if you have seen the news recently, but was recently stated that UK now has halved the CO2 emission with respect to 1990. And this is an effect of this trend that took place from this time and now is going on. But again, we see the problem of low prices, but there is also another issue I think we should consider, the fact that we are considering in general a global problem with a local perspective. What do I mean? Here I'm reporting a very nice chart that was very inspiring for me. That is showing the flow of the CO2 embedded in products. What does it mean? It means that in this case, what we are seeing here, we are seeing the flows of the goods and the CO2 embedded in that goods that move from China to USA. As you can see, there is a lot of CO2 emission that were taking place out of Europe and USA, for example. And they were actually produced to cover some demand in Europe or in USA and Canada. And actually, this amount of CO2 are very relevant. They're around 20%. And according to IMF estimates, for every unit reduced of CO2 in Europe, we have an increase in emission out of Europe of around 50%. So recently, Europe was trying to address this issue with something that we call carbon border adjustment that were reported in Ursula von der Leyen agenda that basically should take into account this effect. So the CO2 that is embedded in the trade. But this is something very difficult to be done from the political point of view and also from the technical point of view. And the expert estimates that we still need at least a couple of years before we include this in the European ETS, at least, because of course it depends a lot on policy, on politics, and this It's not very easy to forecast. So we provide some context to the problem, but what are the analytical tools that are provided by what we call industrial ecology? So the principle behind industrial ecology is trying to find innovative solution to complicated environmental problems. This is probably the most complicated environmental problem at the moment. And it's very hard because we need to take into account all the complexity and cross-sectoral analysis that is including the issue of CO2 emission in this analysis. So we need to take into account multiple sector, commodities, agents, environmental impacts, because it's just not only a matter of CO2. And in order to address this issue, we can divide the tools, the approaches in two different approaches. One are the attributional, that are descriptive. So they are taking into account the attribution of the responsibility beyond the environmental impact. And some other are doing something more, and they are called the consequential life cycle assessment approaches that are considering the life cycle impacts and also the consequence of the introduction of new policy, of new technologies in the baseline case. So we can, here I try to do something very difficult. So considering all the tools that are within industrial ecology so far, but more or less all of them are considering this complexity. This is exactly the idea behind industrial ecology. So more or less all these mechanisms shared this principle. But then there are some tools that are considering time evolution, and some other are not considering time evolution. Among them, we see that among the attributional one, we only have the dynamic material flow analysis that can in certain way consider time evolution. And among the consequential, we actually have, in theory, in some application, it's possible to take into account the time evolution of this. And from the point of view of the agent behavior, some models are better than others from this point of view. But when they are doing this, that are actually considering some other assumption. Every time you consider behavior, you should include a general behavior that should match with real behaviors. It's not always so easy to be done. And I also reported here a very important principle that is actually considering on the so-called technological choice models. That is the comparative advantage principle. And that is something that, as we are going to see, it's very powerful in determining the impact associated with future changing consumption patterns. What is the comparative advantage? Is the idea that the lowest cost producer can provide goods and services until resources are depleted. Okay, this is very simple, not always so shared in economic models, but in technology models, this is more true. Then there are models that are considering high technological and infrastructure detail at product level. This is the case of dynamic material flow analysis and process-based life cycle assessment that are going product by product, building the supply chain behind the product. And I also reported a smaller check sign also in the input-output models, because depending on the level of detail of the input-output tables, we can reach the level of product detail. But we are going to see, because our analysis from today will be focused on input-output models together with technology choice model. What do I mean? And now we are going in the section devoted to a brief explanation of the idea behind input-output analysis. And I would like to start from some historical hints. This man is Vassily Leontiev, is considered the father of input-output analysis. He took a degree in Berlin and then studied in England. And then he moved, he worked in URSS, And then he moved to USA. So he had a very, very multicultural background. And he moved in USA in the 30s, and he was trying to answer questions from political men about what we are going to need if we are going to increase the production of all the material that is needed, for example, for a war. And this is actually a very difficult question, in particular in that times. And in order to answer the question, he developed what is still remembered as the first input-output table for USA. And he also won the Nobel Prize for economics for this. And actually today, all the GDPs, all the gross domestic products are computed from input-output tables. So this had a very important impact. But what are the assumptions behind input-output tables and by consequence also on input-output models, so technology-solid model that are using input-output? That is the case of the case study that I'm going to explain to you. Basically, there are some assumptions that we should always consider when we are using an input-output model. So the economy is assumed that behaves in a consistent manner. What do I mean? I mean that, as we have seen also with my colleague Nicolò Stevanato, a material balance should be respected. The supplied should match what is used. So I shouldn't have any leak of material when I'm picturing all the jurisdiction, all the economy in one unique framework. Not only this, also from the financial point of view, I should also have the same balance. So all the money spent should be matched with all the money produced, all the value produced from some other else. Then there is also now an important assumption that is actually not always true, but in a very high volume for small changes that can be assumed as true, which is the scaling variance. What does it mean? It means that the structure of input doesn't change if you are producing a very tiny amount of a certain product or a very huge amount of the same product. And then there is also the assumption of price invariance. And so when you are considering the input-output flows among different sectors, you are not considering price fluctuation from sector or to sector or time to time. And these are the ideas that are also behind the input-output models of Leontief. I would like to provide you with a brief idea. This may be a little bit, I hope that it will be easy to follow, but this is just to give you an idea of what is an input-output table. What are the information that you can take out of a monetary input-output table? So the input-output table that is representing interaction in monetary units. Here I reported a multi-regional table, and I reported Ethiopia, Italy, and the rest of the world as the countries that are here depicted in the representation of the global economy. What can we find in such a table? From one side, we have the information of technology. What do I mean with technology? I mean what is needed in terms of input from all the other sectors to produce the output of every sector. And this information is found in as a domestic, from the domestic point of view, in the red squares that were rotating. And these are the interlinkages between industries of the same nations, okay? And then we can distinguish actually region by region. And so here, for example, we can have the inputs that are needed by Ethiopia from Italy. So the inputs from Italy requested by the Ethiopian industries. And these are the bilateral trade between industries of two different nations. And here, the next step is related to the final demand. So the same information, but only looking at the consumption side of us as consumers. And the same information can be provided also, for example, if Italy wants to consume something that is produced, me as an Italian want to consume something that was produced in Ethiopia. Okay, and a very important information is related to the role of value added. Value added is basically considering inputs, economic inputs. So the fact that people are working on this industry, the fact that there are some machines that are used in this industry, and these are adding value to the inputs that are transformed in a certain industry. And then, of course, we come to the environmental layers, which are the one that we are interested in. Okay, so here I will find all of what I need in an Ethiopian industry from all the different regions and their individual sectors, and also from the point of view of inputs from labor and capital, and also the consequence on the environment. And in this line are actually looking at who is consuming what was produced by this sector in Ethiopia. Okay, this is basically the basic idea behind input-output tables. But coming back to our problem, why we are using input-output extended with environmental extension, so environmental input-output analysis for a sustainability challenge, in particular the emission reduction. Because we can, in theory, answer to the question how many tons of CO2 could be allocated to different regions of the world using a tool that has the most extended scope. So I'm considering all the economy together. And actually, it's also good for introducing carbon taxes or mechanisms that are impacting on the economy. And what do I need when I make an input-output model? I need information on geographical, sectoral level, what are the impact categories that I'm going to consider, and all the information of the tables that I've just shown to you. So in this case, we are going to consider global economy from the geographical scale. We are not introducing sectors. We are easy. We have only one sector in the economy. And then we are also only looking at CO2 emissions. And so all this data can be provided by tables. In this way, I would have as an output the environmental impact in terms of CO2 in this case. But of course, I could extend this to economic dimensions. So moving to the CO2, this is actually the picture that we are looking at today. If we are distinguishing among two different approaches. So some of you this morning asked, what is the best model to compute CO2 emission? And maybe a very important part of the question, and so also the answer is, how do you attribute responsibility? There are actually at least two different mechanisms. The first is the territorial or production-based accounting. This is taking into account all the emissions that are taking place within the country. Okay, so very easy, and this is also the idea behind the ETS scheme. From the other side, we can have a consumption-based accounting. What does it mean? It means that the countries are responsible for the CO2 emission released all over the world to produce what they consume, okay? And here you can see the difference. For example, in the case of China, we have a lot of emission, okay? But actually, if you consider the consumption-based approach, you have an important difference in negative. And therefore, Europe is the opposite, because we are producing maybe less, but then we are importing a lot of products from other countries out of Europe. This can determine the so-called carbon leakage. This is introducing our case study, which will conclude my presentation. So there can be a carbon leakage, because if you introduce an increase in CO2, in the price of CO2 emission in a certain jurisdiction, such as Europe, you can have an effect of importing more from outside because maybe it's cheaper, but you are not sure that the emissions that are released in other countries are as low as the one that you can provide in Europe in this example. And in the International Energy Agency report of 2016, we provided a contribution exactly on this, showing the differences between the OECD countries and at the time developing countries such as China. in producing, in these differences, so in consumer and producer responsibilities. But the idea behind is that if you want to reduce pollution in one country, it doesn't mean a global improvement. And in the case of CO2, which is, you know, a more global problem, this can have an impact. And you should analyze the supply chain of different regions if you want to consider all the complexity that is behind this model. So this is the paper that we publish on this. And so we took Europe and we had the modeling approach trying to move from a production-based accounting to a consumption-based accounting. So considering this complexity related to the impact embedded in imported goods. So of course, in order to do so, we had a modeling approach. My colleague already talked a little bit about modeling, and you probably already know a lot on modeling. And in particular, in this case, we adopted a model that is taking into account, as I was saying, an input-output table. So an input-output model that can work by itself, but actually we increased the complexity of the model using linear optimization in what is called a world trade model. So a model that can consider the trade of different regions. And what is the idea behind it is a comparative static. So I will assess this shift from production to consumption-based approach with overnight approach. So asking the question, answering to the question, what if tomorrow morning the world is changed and there is moved from production to consumption-based, in particular in Europe? So, so the degree of freedom is not on the technology. You don't have time to change the technology. You can only change the import and export pattern and production pattern among different regions of the world, with the same approach that I was already describing to you, the comparative advantage. So we developed the model, as you can see, as a fair enough representation of the real world that can be used to, you know, designing counterfactual example of what if scenarios. So we started from a case zero. We introduced more and more important reduction of CO2 emission with one scheme or the other. And we end up with, of course, most costly solution, because we are introducing every time a most important reduction in the CO2 emission. But we can have some hints out of this. This are the equation behind the model. And so we are minimizing global cost, because we think that on average, at the global level, what industries are doing is just trying to reduce the cost while satisfying demand and not exceeding available resources, in which CO2 actually here is modeled as a resource. And the other important thing is that we should always have non-negative producing volumes. And this is what it's the result out of our analysis that is concluding also my presentation. And what do we see? We see that a reduction in Europe is actually in CO2 with the production-based accounting mechanism is taking place. And this is, you can see this from the blue reductions. But in other countries in the world, there are an increase in CO2 emissions that at the end of the day are in net, so the global change in CO2 emission is increasing. So you are reducing, very importantly, the emission in one place, and this is having an impact in terms of costs, of the global cost, and also will increase the CO2 emission. So it doesn't seem like an optimal policy. From the other side, the consumption-based approach, at least in Europe, is ending up reducing emission, not only Europe, but all over the world. So preventing what we call carbon leakage. These are the most disaggregated results that you can find on the paper that we published. And here you have the CO2 and here the use of economic factors. You can have a look. And this is going to be different case by case, but in general, we see this pattern. So I'm concluding my presentation with this. I'm open to questions and curiosities. And if you want to have some more detail, you can write me on my email, or better, if you want to take the floor now and ask question, it would be great.
Thank you very much, Nicolo. We can see if we are getting some questions from participants. So it was either crystal clear, or participants are very willing to go for lunch and break now. Maybe
Okay.
let's wait one more minute. And I remind participants that any question you can have, you can send them by email, and we'll be happy to provide answer and to liaise with Polymi colleagues to provide more information. And I also remind that we will send all this material to participants, so you can have a deeper look, and maybe questions will come when you write again.
Yeah, of course. Okay, great. I thank you a lot for the opportunity and also for the attention. And of course, I can still wait some minutes, but if there are no questions, I leave you the floor, let's say.
Okay, thank you very much, Nicolo. It was very insightful hearing from this environmental input-output analysis. This is something really, I think, of high interest. So unless there are questions on this Polymi presentation, since this is the last webinar of our series of webinars with Ethiopian colleagues, and it's closing a first step in our collaboration program, we'd like just to take a few minutes to close properly and explain the next steps. So this is why my colleague Zakia has joined. Hi, Zakia.
Hi, everyone.
So let me share again my screen just to see you that today was the last webinar of so this series we just had over the last days, but it's not over, and we will continue to work together very soon. So immediate next steps. We will send you a very short evaluation survey. Please answer this survey so that you can rate the sessions, give us feedback, and this will enable us to improve the training in the future and to adjust better. Then we will continue having some regular activities together, including some webinars every month, which are not technical webinars teaching how to do statistics and how to do modeling, but which are more informative webinars, as we did in the past. So it's every second Thursday of the month, presenting a key report or presenting analysis from IEA or from partners. Save the date. Next one will be on the oil 2021 market, very recently released by the IEA, where our colleagues from the oil market team will present how this key commodity and how this key energy has evolved in the year 2020, and what is the prospect for the coming 5 years. So this is not long-term projections, it's more short-term projections, but it will be very interesting and we will focus on the Africa situation. And in parallel to those regular these regular webinars, we will continue discussing with you through the WhatsApp group. So if you're using WhatsApp and if you're not yet in the group, please reach out to us. We'll add you to the group, and this is a good way to share information. There is also a LinkedIn groups where we will increasingly post information on global energy trends, on African findings for the energy sector. And we would be very, very happy to hear from you and hear your contribution as well. And last but not least, as soon as travel restrictions will be lifted, we will be very, very happy and looking forward to coming to Addis and to do some face-to-face training with you. So this is the plan for the next steps. If you have any question, please feel free to ask. We were very, very happy to have you during all those sessions, honored to have all of you attending, and His Excellency the Minister doing the opening in last July. And you can see that I've been joined by Gianluca, Zakia, that you have seen and heard a lot during those webinars. I just put the photo of our colleagues that could not come today for the closing, but who also are joining us to thank you for your participation and to say that we are at your disposal for any question, and that we will be in touch. Zakia, Gianluca, I let you add if you want to do.
Thanks, Arnaud. And I just want to say thank you again for staying and having been constant over the past few days. Thanks for your dedication. And I hope that this training has been useful to you. And again, do not hesitate to contact us if you have any questions on any of the training material or on in any way that we can help you in your work to improve energy statistics and develop your models. Thank you.
Well, I just wanted to say congratulations to all of you for all this long course that we started last year, and it's finally finalized with a lot of good topics that have been touched. And so, sorry, I was muted. And I'm looking forward to communicate again with you on these topics. And if you have any questions on statistics or modeling, don't hesitate to contact Arnaud, myself, Zakia, or all the colleagues that you have been working with. So looking forward maybe to come to Addis, as Arnaud said, to meet you in person, because I think this will be a game changer in our relationship and in the exchange of experience. Thank you very much. Arnaud, we cannot hear you.
Sorry, thank you. Okay, so thanks to all of you, and also thanks to our Polymi colleagues for this very interesting session today. Thanks to you, Francesco, Nicolo, and please pass the thanks to Emanuela. I think it was both complementary and echoing what we've taught the participants on how to do modeling, but the topics you put spotlights on were very, very interesting, and again, complementary to the teaching we had. So we are looking forward to continuing this collaboration. And as we will move to the next step with Ethiopia, we will be happy to continue working with you, Polymi, and doing more hands-on and practical session on some of the tools you have developed and shown, as we will do on some modeling tools developed by the IEA, and of course on the statistical part with all our statistical team. So I think it's really time for lunch for you in Addis. So thank you very much for your attendance, and looking forward to talking to you again soon.
Thank you very much.
Thank you.
Thank you all. Bye.